So today, what we're going to do is we are going to go over the practice exam for our for 2168. Geez, I am tired. I am trying to work without caffeine in general because seeing how that helps other things. The answer is, you think you get enough sleep, but you don't. Okay. So I've opened up IntelliJ just to have that open, and we are going to go ahead and make sure that this works. All right. Once again, it will be out of 105 points.
All the bonus points.
Mm-hmm.
Well, I actually made it on time.
First page of the exam will look a lot like this, which is, I believe I have some extra notes here. I may or may not. Again, you're allowed a cheat sheet, you know. So first page will have 4 questions just like this, as far as you know, what is the best data structure from the list over here. So you need to model which patient should be seen next at a hospital. Patients should be seen in as close to order of arrival, but patients with more severe situations should be seen first. This is exactly what I went over in class. That is a priority queue. A router needs to hold packets in a buffer and deal with them in the order they appear. All right, that would be a queue. Now, if you were to deal with them in the most recent one as opposed to the one that's been waiting the longest, that would be a stack, right? First in, last out in that case. You need to model a hierarchy. Now, that would be a tree. Trees are great for modeling hierarchies. If you're not using binary search trees are very specific forms of trees, but trees in general, you see those all the time when you see org structures for various companies or like. Let's see. All right, you need a data structure to hold your previous decisions in case you need to backtrack. That's a stack. So a lot of times, notice that I do leave these blanks. I do not need you to justify your answer, but if you feel like, I gave you space to justify just in case. And if you do justify, you know, if I can follow that logic and it's not completely wrong, I can always get partial credit on a wrong answer. All right. For the next section, which on the exam, it's pretty much going to be very, very similar to the stuff you had to do with the quizzes for trees, right? The online quizzes that I let you take for again and again. So here we see just some kind of similar questions. A node at the top of the tree is called what? We could call, that's the root. That one is one of the few unambiguous answers that we can give. However, for B, C, and D, I'll accept a lot of different answers, okay? Because the links from a node to a successors are called what? Well, links for one, obviously, but edges would also, you know, is typically what we look for. The predecessor of a node in the tree is called a what? It's called the parent. Right? But also the predecessor, you know. Yes?
Would you accept ancestor for that one as well?
Ancestor is more general. I would give half credit on an ancestor because that is a much more generalized answer.
Okay.
No, nodes that have the same parents are what? Siblings, yes. We exploit the English language here in order to basically just be able to use these family terms. Describe without using code how to calculate the height of a tree recursively. All right? The height of a tree, as I mentioned, is basically going to be, so we have some tree. Actually, let's go ahead and genericize it, right? We have some tree, and we have, it has its, you know, two subtrees. Right? So how do we know how tall this height is? Well, first off, this could be ostensibly 0. If this guy is 0, right, then the height of the tree is whatever the height of this is plus whatever the height of this is, right? Let's go ahead and denote that x. Well, my height is always 1, right? And then if my right subtree is 0 or my left subtree is 0, I take it's going to be whatever the height of the other one is, right? Just kind of, let's assume I have a magic function that tells me how big a tree is, right? Similarly, if we expand this out and say, okay, now we've got an x and a y as opposed to an x and a 0, right? The logic still holds. We would just simply add either x or y, depending on which one is bigger, right? So what I would say here is, to describe using code, without using code, how do you calculate the height of a tree recursively? The height of a tree is equal to 1 plus the height of the left subtree or the right subtree. Whatever one is bigger, we just take that, add 1 to it. And then that subtree will then obviously have to do the same. All right, as I mentioned, this one is drawing an example of each of the possible types. Again, drawing a circle would suffice for all of them, which is why I say use a different example. So a full tree, again, is a tree where we have where every node has either 0 children or 2 children, right? I'm going to skip to a perfect. Perfect trees are trees of 2 to the height that are of height h, and they have 2 to the h minus 1 nodes. For binary search trees, this is only one possible configuration, which is if I were to ask you to draw a tree, your instinct would most likely to be to draw a perfect tree, which is a tree that is perfectly balanced, all the same exact format on the left and same exact format on the right.
So basically symmetrical. Draw a line down the middle, see if it matches up to the left side and the right side. Question?
Yeah, should we know that formula for the exam?
No.
Okay.
No, it's just an easy way to remember, oh, there's only one possible way for a tree to be perfect, and of each height. Complete says that we have a perfect tree up to some height, and then we go left to right across the bottom without any gaps. A complete tree is what we draw for heaps, right? Heaps are always complete trees. Okay. All right. This one is, I remember, this one is always kind of just always looks a bit janky, but we'll live through it. So we go one at a time. So the first item, whatever you add, that is going to be the root, no matter what. Okay, that is a weird 4. Okay, 42. Okay, so 10. 10 is less than, so it goes to the left. 50 is greater than, so it goes to the right. We always start at the root when we're inserting. 12 is less than 42, greater than 10, so it goes over here. 17, less than, greater than, or I should say less than, greater than. Ooh, there we go. 42, I hit a keyboard combination I didn't know existed.
Behold, Windows.
Oh, I mean, like there's a link there. I believe there's a LinkedIn hotkey or a keyboard combination.
Really?
Yes.
That's weird. Like, man, I wonder how much LinkedIn had to pay for that for the next Microsoft bill.
None. Microsoft owns it.
Good point.
You know, the advantages of conglomerates, you know, they get to try to force you to be in an ecosystem. So 80, we put there. Negative 12, right? Negative 12 is a very small number, so it's going to be less. It's the smallest number we've seen so far, but so it goes all the way to the left. 100. 100 is greater than 42, greater than 50, greater than 80. 100 goes over here. Okay. 86.
96.
Oh, sorry, 96. My bad.
Sorry.
Yep, that is doing something like that is your most likely error during the examination, which is why you want to kind of maybe do step by step every so often. All right, and double check your work. 100, 96. 96 is greater than 80, but it's less than 100, so it goes over here. 105 goes over here. And now we've got 86 which is going to be greater than 80, less than 100, less than 96, and then we've got 72. Whew, okay. What a tree. All right, draw what happens, using the previous answer, we'll draw what happens when you remove the following. So, first thing we want to do is remove 42, which is very typical of me to ask you, hey, let's remove the root. Okay, so what we're going to do over here is that we would remove this. I really should have done this on the whiteboard kind of thing, but whatever. But to remove 42, what we do is that we find the next in order predecessor. You're more than welcome to use the next in order successor, but you just want to be consistent because you're doing multiple removes. So that next in order predecessor, that means we are looking for the smallest thing, the biggest thing in that's smaller than it. So for 42, the biggest thing in the left subtree that is smaller than it is 17. And we know that because we go 1 to the left and then we go all the way to the right. Okay? And so 17 has to be that. So we replace this with 17 and instead we just delete the other 17, which is always guaranteed to be an easier operation because of the, just because, okay. It's always guaranteed to be an easier operation. Okay, come on. I don't want to select it anymore. Jeez. Okay. Oh my gosh. Doesn't really.
It's got a mind of its own.
Yeah, well, we are going to, you know what?
You want to draw one real quick?
No, I'm going to go ahead and just simply cheat. I'm going to cheat, assuming that Windows will let me cheat. And I'll open it up in a completely different app.
Good point.
So,
I mean, hopefully their apps work together.
oh no, I just copied. I took a screenshot. So the screenshot's in the clipboard,
Nice.
and there we go.
Uh-huh.
And now we can go and do thickness and white. And there we go. We'll remove this. So there's 17. So we've removed 17. The next item to remove, according to this, is 12. 12 is an easy node to delete. We just simply delete. It has no children, so nothing special needs to happen to it. Okay. Next one to delete is 17. 17. So this is a two-parter. 17, as we see over here, is the root. So we go 1 to the left and we go all the way to the right. All the way to the right, though, doesn't really get us anywhere. So we remove, so our 10 is our target here. This is part of the reason I have this one. Now to remove 10, so we're going to replace 17 with 10, but we need to remove the original 10. Okay, now removing the original 10, that's one of our simpler cases where it has either 1 or 2, it either has 0 or 2 0 or 1 children. This case it has 1 child, so you tell the grandparent to adopt the grandchild. So in this case, the new 10 will adopt -12. And we just can simply, and that's easy to draw here. We just simply draw it like this, right?
Mm-hmm.
Okay, now, last one, 96.
Oh,
Similar over here, 96, right, is very similar. We just simply remove 96, and we have 100 adopt 86 in that case. Okay, doing a removal like this ensures that the cohesion of the tree always takes place. One last thing to note: if we were to delete 80, let's see. We would be promoting 72 up to there. So again, it doesn't matter. My examples were all on the top root, but remember, it works for the root of a subtree as well. Which of the following is the pre-order traversal for a binary search tree with subtrees, TL and TR. So now notice that basically if you remember, the only real difference between them is where the left always will go before the right in post, pre, and in. So this guy over here processing the right, because this one's out because we see it has processed the right before the left. That doesn't happen in our trees. So here what we do is that it all depends on where the root node is processed. Is it processed before everything, after everything, or between the left and the right? If it's between the left and the right, it's in order. If it's before, it's pre, right? Before, pre, and if it's after, it's post. So B is our answer. And then C is the answer over here for post order. And just FYI, in case there's issues with like you accidentally mark multiple answers, I occasionally have a malfeasant student who tries to game the system, and so I just simply go with the rule of your top answer is the one that I take. So the one on top is the one I take, and that just simply.
So no metagaming, guys.
I metagame back.
Mm-hmm.
Min heap. Okay. This one is, well, again, so first off, on the exam, for this one, you'll have one, it will just have different numbers. You can make, so it's easy to create your own practice exams, practice questions. Again, ask ChatGPT for questions. The ChatGPT is very good at generating questions for you these days. Although you might have to wait because it's busy, busy generating a bunch of Ghibli images for everybody, apparently. So.
Oh, I tried the other day because I was like, man, wouldn't that be cool as a profile picture? Miyazaki's basically gonna work.
It's an affront to life itself, is what he said.
I know.
He's very opinionated on it. I don't blame him.
I don't either. It's gonna take my door down.
If you haven't been able to figure it out, I like using AI for generating some quick pictures. The entire our course picture was me basically using the prompt illuminated manuscript data structures.
I think you have a resistor in there. I think it got it spot.
And so it looks like some Gregorian monks stumbled across the transistor diagrams and tried to do them from memory in an illuminated manuscript, because it's completely incorrect. But hey, it looks fun. All right. So now for this one, and this one though, I will give you a actual tree here to work with, as opposed to working off your previous answer. That way, it's less of a headache for me, and that way you don't have to rely off your previous answer being correct. This question, again, heap will be pretty much exactly the same. So here's how it works. We're going to draw the tree structure. I say you can't ignore the underlying array. If you want to work on doing your heap like this, 8, 10, 50, and then we have to do 20, and then I have to do 1, and 1 is the child of, let's see, 8 to D. And so 10 is 8, 10, 50, 20, 1. 1 is the child of 10, so that we swap here. If you want to work like it like this, yeah, go ahead. But I highly recommend against it. Instead, I recommend doing the tree, visualization of it, which is that we add things. Now remember, these are min heaps. I'm not going to try to trick you by saying it's a max heap. All right. Although if I were to give you a max heap, the easiest way to deal with that is just simply draw a 1 over all of these, and then you can pretend you're dealing with a min heap again. All right. So again, so the rule for min heap is that just simply the heaviest items sink to the bottom and the lighter items bubble to the top. So think of them as weights, right? So 20 over here will go over here. We just add at the bottom. It does not need to bubble to the top. Okay, 1, again, everything, rather than adding on the root like this and going left and right, we add things at the bottom in the next spot that would keep the tree complete. And then we let things sink to the bottom and float to the top. 1 is less than 10, So over here, we will replace the 1. And then again, what we would do over here is 1 would be over here, and we'd compare it to its parent. 1 is lighter than 8, so 1 floats to the top. 1 goes over here, and 8 sinks down over here. So now it is 1, 8, 50, 20, 10. Okay. 4 will go over here. Here, 4 is lighter than 50, so 50 sinks down. So we've got a 50 over here now. And a 4 goes over here. 4 can't float to the top anymore because it's heavier. And then we go to 3, and then we add 3. And that will swap. So we'll end up with 3 and 4. I kind of deliberately designed these ones so that it's hard to incorrectly do it. In the sense that, like, if you give me an answer and it's the correct answer, you couldn't have arrived at the correct answer by incorrect means. All right, using the heap you drew above, draw what happens to the heap after removing an element twice. All right, so what we're going to do over here is, that was the issue last time, I think. Yeah, the issue last time was I did that. So let's go ahead and so this one was, 1, 8, 3, and then 20, 10, and then 50, and then 4. How was class today, honey? Oh, it was great. My professor effectively drew his answers in crayon. Sorry, I just have fun with these settings. If these settings exist in the whiteboard, they should be used, obviously. All right, so to remove the root, what do? We will, to remove the root, well, the first thing we do is remove it, but then we have an empty space here, and complete trees can't have an empty space. So what do? We replace it with the only item that we can possibly move, right? The only item that can be moved and can maintain this tree's completeness is the very last item, which is 4. Because, again, we remove 4, or we move 4 to this spot, and now it's at least structurally sound. So we've removed it, but now, as you can see, that now we have to fix the heap features, the heap definition, which is saying, hey, the smallest item should be at the top. Okay, so what we do here is we compare 4 against its children, 8 and 3, and we swap. And if it's heavier than one of them, we swap it with the lighter of its 2 children, right? Obviously, it's only heavier than 3, so it should swap with 3. But if it was 3 and 3.5, right, we'd swap it with 3, because we would need whatever was on top to make sure that the heap property stays, valid. So 4. So what we'll do over here is we take 4 and we take 3. And we have 3 and 4. Now we do another remove operation. This remove operation, again, we are going to remove 3 because I'm not specifying what we're removing, so we're going to remove 3. And so 50 is going to go here. Okay, 50 goes here. I could just use an eraser, but hey, why not? So now we've got, yeah, why not? Could you? Okay. So now we need to make sure this heap property is maintained. So 50 is heavier than both 8 and 4, but 4 is the lightest. So 4 will go over here, and 50 will go over here. Okay. This is probably the hardest part of the exam for a lot of students, the Huffman coding, or the hardest non-coding portion, I should say. Okay, which is, I give you a frequency table, right? I've given you a document, and you're trying to figure out what the Huffman coding is so that you can compress it. Obviously, this is not obviously. This is just a ridiculously small set for these things, right? where we have A 50, P 40. These are small counts. You'd be wanting to, if you were doing compression, we'd have like thousands of characters to count. But it's easy enough for doing this contrived math example. We want to draw a Huffman tree of these frequencies, okay? And that involves arranging these symbols into a priority queue and then merging them together, okay? So follow along. So let's go ahead and figure out what our symbols are. We had A, so we had A is 50. P is 40, so P will go here. L is 20, E is 60, E 60, L 20. And again, I'm arranging them in numeric order, as you can see. And X is 1, okay? And I did it in this order very deliberately for at least constructing this tree. So we have this, so we have each of these. They kind of are nodes that just exist by themselves, and every node has a symbol and a weight, okay? But we basically need, but they exist by themselves and they need to be combined into one tree. So what we do is we have this priority queue, and while the queue has one thing, has more than one thing in it, what we're gonna do is we're gonna dequeue twice, and the first thing we dequeue is gonna be the left, and the second thing we dequeue is gonna be the right, okay? So we dequeue these two guys. Remember that the weights are 20 and 1, okay? Okay, we dequeue these two guys, X and, let's go ahead and L, okay? And what we do is that we take two nodes, we take them and we combine them into a single node, X and L, but they have a combined weight of 21, right? That's what we do. The next thing we do, and now what we do is that we take this and we take this combined node and we put it back in. So I'm going to go ahead. So we take X and L, put it into this priority queue, but it's a priority queue. Here and here, the smaller numbers is the top, is the head of the queue. So instead, what we do is we skip this all the way to the front because it's smaller than everything else. 21 XL. Okay? The next thing we do is, while the queue is not empty, we dequeue twice. So we are going to grab 21 and, we're going to grab XL and P. XL will be on the left, P will be on the right because XL is first. So over here we have P, and we combine them. Now P had a weight of 40, so this has a combined weight of 61, correct? Mm-hmm. All right. So the next thing we do is that we put this combined thing, XLP, into the queue. It has a combined weight of 61, so it stays at the end. So you can see that the contrived example here was specifically so to show you, hey, sometimes it goes into, sometimes it moves to the front, sometimes it doesn't. Okay? Next, we do A and E. A is, so we dequeue A, we dequeue E. Now, they don't have a node, right? Sorry, right? Neither of them are a combined node, so we just kind of just start another one on the side to combine them. A and E. And they had 50 and 60, I believe?
Yeah.
Yeah, 50 and 60, 110. Combined weight of 110. We put that back into the queue, A and E. And now we're nearly at the end. We have 61 and 110. 61 goes on the left because it's first. 60 and 110 goes on the right because it's second. They'll have a combined weight of 171, but that doesn't matter anymore because we're done. Right? So here is our resultant tree. Any questions about that? Right? You dequeue, you combine the nodes until you have only one node left. For the answer, by the way, you can keep that combined weight in there. I was mainly adding it as a visualization, but you don't actually need those in there. That's not important to the problem, that combined weight being visible in the tree structure itself.
It's just going to help you put the tree together out.
Yeah, it's important over here for the, it's important for these, for putting in the queue. Okay. Now, the next part is, if you do this first part wrong, I will assume what you have for that's fine. I'll assume what you have is correct for the second part, which is encoding the string apple into binary using this encoding. So what we do is that we label each of the branches. Each left is a 0, each right is a 1. Now, typically what you could do is so I have two ways of asking this question. The first way of asking this question is giving you this. The second way of asking it is giving you a bunch of strings of zeros and ones and asking you to translate that. If I were to give you a bunch of strings and if I were to give you a string of zeros and ones, like translate 0, 0, 0, 0, 0, 1, what you would do is you'd start at the top and go until you hit a symbol. 0, 0, 0, 0, 0. Oh, that's an X. So, and then I would go again. 0, 0, 1. Oh, that's an L. I guess the answer is XL. The other way to do it is you can either like reverse translate them. Like you can say X is 0, 0, 0. Sorry, for translating apple, you could do X is 0, 0, 0. L is 0, 0, 1. Or you can just simply do it, what I'm going to do, which is simply look, okay, find an A, which is viable for these smaller questions. Find an A is 0, 1. Find a P is 0, 1. Sorry, A is 1, 0, my bad. P is 0, 1, 0, 1. L is 0, 0, 1. And E is 1, 1. So that would be our answer. 10, 0, 1, 0, 1, 0, 0, 1, 11. Okay. Now, for our... Oh, we are making great time on this practice exam. I'm just speeding along. Okay. Write a method. Oh, yeah, because I do the extra coding problems. Right. So, coding. Write a method which, given a root of a tree or subtree, computes and returns the number of nodes that in the tree or subtree. You may not use the size tree method, but it even exists to begin with. So for this problem, I'm going to do some, so for this problem, I'm going to create a tree class, and I'm not really going to add anything into it. Again, I'm not going to have, everything I'm putting in here you don't need to have. I'm specifically making it so that I'm just not going to deal with compilation errors. So public node, public would be a private class node, and it would be, and then we would have and yeah, that's pretty much all I need except for the variables. I need also, let's go with E extends comparable E, and a node will have E, and then we'll have E item, node E left, node E right, and that's probably everything I need. Oh, right, and then of course what I need over here is, I may not actually need to have it declared because of the way our problems work, but node E root, that'll work. All right, public size tree. So this is just simply forcing you to do this in binary, sorry, non-binary, do this in recursively. So, which is saying here, given the size of the tree, given the root of a tree or subtree, compute the size of that tree. Right, and actually in reality, you'd probably get something like this, int public static e int, and then you'd have this method call, basically would return size tree this dot root, right? Typically, with recursive methods, it looks like this, where you have a public accessor method, and then wouldn't be static. This dot root, where you have a public accessor method that would call a private method. The reason you typically don't have a private method that takes in that you don't have that recursive method exposed is because you don't want the programmer to accidentally try calling it in the middle of a recursive process. You generally want the recursive processes to run from the top down and not start in the middle of something. But we can ignore that for right now. What we're going to do here is we are going to just simply do it as simply as possible. Int and node e root. So the size of a tree, let's see. So how do we compute the size of a tree? Well, again, let's draw it. Okay, let's kind of go through. What we have to do is we have to go through our, whenever we look at trees for base cases, we have to look at just some very basic cases. First case is if the tree looks like this, which is to say nothing, right? If the root of the tree is null, if there is no tree, that's very easy. Nothing, here, if we have nothing, then the size would be 0, right? On the other hand, if we have a situation like this, where we have a node, and then we have either a left subtree or a right subtree, right? It'd be the size of the left, and then and then plus 1 for us, right? In fact, because we know the size of an empty tree is 0, we can actually reduce this to saying, hey, the size, given a tree, the size of the tree is 1 for myself, plus whatever's in the left subtree, plus whatever's in the right subtree, right? And if it happens to be empty, I'll just get a 0, and adding 0 is no problem. Make sense? So this actually comes out really straightforward. So what we do is we first check to make sure that we don't have a base case. If root, or we check our base case. If root equals null, right? If this is empty, oh man, I'm typing so great today. If root is empty, if we don't have a root, we will go ahead and return 0. We have nothing. Otherwise, we don't even have to bother writing an else. We don't have to do anything, right? We can split this. I can split this up and say, hey, int left size. I could do it like this. Int left size is equal to root size tree root dot left, and then do the same thing for the right subtree. Right, I can write it down like this so that I can think through the steps. I could even do int self is equal to 1. But at the end, all I'm going to do is int left size plus 1 plus right size. And there's nothing stopping me from instead just simply not having lines 14 and 15 and just simply doing size tree left plus 1 plus size tree right. And it just depends on what you find to be the most readable thing. This tree dot. Why is it telling me? Oh, yeah, we'll need to make node static. There we go. Okay. So this one, again, is going to be easier than, it's a good warm-up, but it's easier than what we're going to see in the actual exam. Let's go ahead and see something that might be more difficult. All right. Write a method which, given a tree, returns whether a tree is a full tree. Okay? So, we're checking to see if the tree is full. And a tree is full is that if you have no children or you have 2 children. Now this is a bit different because it's kind of asking for a global quality of a tree based off of one node. But we can figure that out though, which is simply saying, well, I've got this tree, and I know if my left subtree is not full, then this entire tree can't be full, right? Same with the right subtree. If this is not full, then the entire subtree can't be full. Make sense? So we can ask our subtrees if they're full or not. And otherwise, we can just simply think about our base cases first. Now, our base cases are actually, we can make a lot of determinations off of this. Public, static, Boolean is full, root, no, okay, that's what my fingers were trying to do. Node root. So I ended up, okay. If root equals null, this is almost always a good check to start with, checking if root is null. Because then we can make a determination. If the root is null, I guess it's empty, so return true. That's technically full, right?
Because it's
It's em-
okay, like I see what you mean.
So if it's empty, right, if it's not there, then it has no children. So I'll return true, I guess. So now we know I'm not null. So we can make some determinations right away based off of whether I have a left subtree, if I have no children or not. So if root dot left equals null and root dot right equals null, right? So I can actually go ahead and just check my children and see if they're null. And I know if they are, then I know I can return true. So we might not ever actually hit this, but this is a good thing to have. So if the root of the tree, so basically if I know that both my sides are empty, then I'm a full tree. So I can return, yes, I'm a full tree. Now we just do some copying and pasting and change it to not null. So if my left is not empty, so if I have a left subtree but no right subtree, that means I have one child. Return false. Similarly over here. And even though I shouldn't need to, I'm going to go ahead and make these else ifs, right? Just simply because that's easy to understand that these are all conditioned upon each other. So if left subtree, if right subtree, and then finally, else. What if both of them are? What if we have what if I have both my children? Well, that means I'm probably full. But what I need to figure out is my left subtree full and my right subtree are full. So that ends up being actually very quick to return, but that ends up being our recursive call. If is full root dot left and is full root dot right. So if I have a left subchild and a right subchild, what I need to do is I ask, is my left subchild full, and if my right subchild are full. If that is true, I use the AND operation to combine them together, and as long as both are true, then I'm full, so I can return that. But if one of them is not full because they hit this case, then I'll have to return false myself. Make sense to everybody? All right. Equals. Write a method which so this one again is, you can see over here, extra practice, 0 points. So if you were timing yourself, right, this one was meant to be a bit harder, a bit trickier. Also, it's a bit more ambiguous. Write a method which, given two trees or subtrees, returns whether or not the constants of the entire tree are identical. I tried to be unambiguous here. Do tree A and tree B store the exact same data in the exact same way? So in other words, not only are they equal in terms of what they have, but their structures are equal, right? You could have two trees that have the same contents, just differ based on how you add things, right? For instance, you could have a tree that does 1, 2, 3, and then you could also have the tree be like this, and they'd have the same contents, but they wouldn't be equal according to my definition. Make sense? All right. Okay. Public static Boolean equals, and then I'll go ahead and just call them root instead, because we were doing that. Node E root A, node E root B. All right. I'm just going to put a return true here, but we might delete it later. So first thing we should check is, are they null? In fact, we can kind of check that together. In fact, checking if they're null versus not null gives us a lot of information right off the bat. So for instance, if root A equals null, and we could probably be more clever about the way this formatting, like if root A equals null equals root B or something like that, but then it's easier to do symmetrically like this. So if they're both null, I'm going to return true, because guess what? They're equal, right? Great. Next, what are we going to do? I'm going to go ahead and copy paste this. And modify it. If root A is not null, or root B is not null, basically saying, okay, if one exists but the other doesn't. Well, if one exists but the other doesn't, return false. Okay. Now we're going to check. Now there's a couple different ways we could go about this. So now they both exist. We know we're in a state where we know they both exist. So there's two things we need to check. Are the values they hold equal? And are there subtrees? And do their subtrees have the same structures? So let's address those one at a time. If, else, if, and there's a bunch of different ways to do this. I'm just doing this a different way than I normally do. Else if root A dot item dot equals root B dot item. So if those two items are equal, yeah, why don't we do it like this? If those two items are equal, then we're going to check their structure. But if they're not equal, return false. Make sense? Right? If they don't have the same items, we'll hit that else and we'll return false. I was thinking about doing it as basically if they're not equal, right, then return false over here. But honestly, just reading through it like this, the conditions make more sense than doing it in the order. It's one of those judgment call things as to how you want to do it. Okay. So, we know the items are equal. Now we have to check the structure, which we basically need to say, hey, is the left subtrees equal and are the right subtrees equal? So we just do that recursively. Return equals root A dot left, root B dot left, and equals root A dot right, comma, root B dot right. And then that will check, hey, are those two things are those two structures equal to each other? It'll also check their values. Because that's what we do over here. So, but a lot of these things, you work through them by thinking about, okay, what are the base cases? And then sometimes you might have to think, okay, what if my left child is null? Is that something that's taken care of automatically in this case? Or do I have different cases based off of whether or not I have one child and on one side but not on the other?
So what you're saying is the goal is to do the most like simplistic base case, like cases that you have first, and then
Yep.
start working your way into the more like, hey, what if?
And
kind
then
of
the
situation.
recursion generally is just basically an if statement and then recursive calls, possibly with an operation like an addition or an and. Now, I should mention, you don't have to solve these recursively. You don't have to. No, I never said you had to write a recursive solution. However, it's a lot harder to do it not recursively. And you're going to effectively be doing it with recursion because you'll probably have to use a stack to kind of store and to backtrack. So that, and doing it recursively just simply works for a recursive structure.
Less lines.
Mm-hmm. A lot easier. All right, write a method that returns what character occurs in a string and how many times each occurs. So if you've done 1051 with me, you've done this problem 1.5 million times. Well, more like a few. Public static map character to integer. And then that would be, what is it? Yeah, just count. And string, rather than word, I'm gonna call it text because we're probably actually counting the string that as it occurs in more than one word. Yeah, returns what characters occur in a string and how often how many times each occurs. So, first thing we do when we're doing a counting problem is that we create our counter. And also, that's what we're going to be returning. So we were going to create the thing we return. So I'll call it count, even though that's the name of the method, but hey. New hash map, right? Remember, map is the interface. Return count. What we do over here is we want to count how often each of these occur. So we're going to iterate over every character in the string. So car C, I'll go with car letter in the text for every letter in the text. Except, now if you do this, I'm on an exam, I might be very generous and not even deduct points. But it does get a compilation error here because it should work. And for the life of me, I don't know why Java just doesn't let this work. I don't know why you can't have your strings be iterables. It makes no sense to me. So you have to convert your string into something that is iterable if you want to use a for each loop, which means you have to do dot to character array. The other alternative is, once you find out that that doesn't work, is to do this for int I equals 0, I is less than, you get the idea, right? To go index by index. I hate doing that. So 4-letter in text to character array, because I don't care where the indexes are. Well, I don't care which one we look at first. I just care, have we done this? All right, so I'm going to show you a couple different ways to do this. One is the generic way that should work for everything. The other way is going to be the more Java way to do it. Okay. First, the generic way to do this is asking, hey, if count dot contains key letter, and you can either do not here. You can either do the not. I like to do the not first. So if it does not have it versus does it have the key. So does it not have the key? Okay, if it doesn't have the key, that means then we haven't seen this letter before. So we would go count dot put letter 1 because we've seen this exactly once, right? Okay. So if it doesn't have the letter in there yet, we put it in. Otherwise, we have seen the letter before. So we do something like this. Int previous is equal to count dot get letter, get the number of times we've seen that letter. And then we would do count dot put to update the count of that letter. Letter previous plus 1 because we've seen it one more time. Make sense? So if it doesn't have the letter, add it in once. Otherwise, we've seen it more than once. Of course, you could make this much harder to read and much more concise by taking this out and just simply doing method calls inside method calls. Right? You can do this. Nothing stops you. But this is easier to read and more clear, I feel. Now, the other way that relies off of more Java methods, because Java sometimes has some very useful methods built in, is basically just simply use this portion. So we would do get the letter and just simply update the count. But if it doesn't exist, we'll get a key error, right? If we haven't seen this letter yet, we'll get a key error. So Java has a very useful function called count.get or default. And it will look something like this right now. So what it's going to do is that it's going to do get normally, except when it hits a key error. If it has a key error, rather than giving us a key error, okay, instead what it will do is that it will, instead of erroring, it will instead return a default value. In this case, 0, right? Which is what we would want to say if I haven't seen it before, right? So int previous, get the number of times I've seen it. I've seen this letter, which will be, and this function will return either the number of times I've seen this before or 0, which is also the number of times I've seen it if it would return 0, right? Make sense to everybody? And so suddenly this is reduced to 2 lines of code for that portion. Make sense? So that can be very useful, the get or default. A lot of times for the default here, you would want to do 0 because that's the count. If you were doing this in the hangman problem that you're currently working on, that might be something like new linked list over here, right? Where you would want to, if we haven't created a list for this yet, let's create a new linked list. Here we go. So that is that. I'm going to skip this and instead go to the analysis. So what are collisions and hash tables? Why do they occur and how are they handled? Okay, so collisions and hash tables. The idea here between a hash table is that we have some magic lookup function, right? The idea is that we have some magic lookup function. We can say, hey, we can take this key and we can convert it into an index. And so given this key, I can find what index we are at. I can find whiteboard. All right, we have a magic function. Given a key, we can take this key and use the hash function and a bit of modular arithmetic to give me the index. We can take this key, convert it into an index in constant time. That is the entire goal of this, right? We are constrained by one fact. The size of this space is infinite. There are infinite number of keys usually, right? Infinite number of numbers, infinite number of strings, right? Typically, we're not dealing with a constrained set for a hash when we're doing this. The size of this, however, this is going to be some kind of array, which, while it can be quite big, will not be infinite. This means that we are dealing with something in statistics called the pigeonhole principle. Anybody familiar with that, the pigeonhole principle? How many people have not heard of the pigeonhole principle?
To be honest, I didn't know until I went to data structures.
The pigeonhole principle is possibly one of the stupidest proofs ever because it is very straightforward, which simply says if you have more pigeons than pigeonholes, then two pigeons are going to have to share the same pigeonhole. That's pretty much it. It is basically the mathematical proof for something that we know, which is that if you have more things than slots, two things, if you're gonna put all your things into a slot, then logically you need to have two of them share. So collision means that basically that since we have an infinite number of keys, an infinite number of them are going to want to go to the same index. An infinite number of them. Now, the hash function, assuming it is well designed, which it is, but it's often not always well designed for your purpose, for the purpose you want. For instance, part of my research was looking at the SHA-256 hash, and that was often used as kind of, was it SHA-160? It doesn't really matter. It's a secure hashing algorithm. And that is just used for security purposes to verify that, hey, this file you're downloading is the same file that you were supposed to download. What you do is you take this file, you throw it into a SHA algorithm, you check what's posted online, and if they match, then those are the same files.
Basically a checksum when you're downloading a program.
Right? Did some hacker go in there and change stuff around? And occasionally hackers do. This happened with Linux Mint, actually, a number of years ago.
I used Linux Mint.
A number of years ago. It was very quickly resolved. Now, in this case, though, because it was designed for that kind of security purpose, it wasn't necessarily evenly distributed. You'd get clumps of numbers if you were using it as kind of a random number function. So these are not random number functions. These are functions that try to distribute stuff evenly, but it doesn't always work depending on the function. But that's an aside. Assume, for the sake of argument, that it does work and it's beautiful and it will basically evenly distribute things. That means that basically that at some point you're going to get a collision. A collision is when you take two keys, right, where you have key A and you have key B, and they're both going to end up at the same slot, right? They're both trying to get to the same index, right? Now, typically what's going to happen is that, though, you know that they have the same key because one of them is actually already there first, right? A is already in the slot, B is trying to go in, right? That's a collision. So collision more specifically would be when you're trying to assign something to an index that has already been assigned. Now there's two ways to resolve this. That was a very long-winded explanation to get you your one sentence answer. There's two ways there's a few different ways we resolve this. The first is open addressing. And another one is is depending on your textbook or who's talking, is called chaining or buckets. These are not the exhaustive these are not the only methods. There are other methods for resolving collisions. Some of them are academic, some of them are more well used than others, but these are the ones that are taught in data structures because they're easy to understand. Ones that aren't taught in data structures are things like cuckoo hashing, which I enjoy because that is a reference to the cuckoo bird, which kicks out the babies of other birds out of its nest and instead lays its own egg in there. It is fascinating. Anyway, cuckoo hashing, that way that works is that, oh, you're in my spot, get out of my spot.
Just gets it done.
Another one is double hashing, which is basically saying, hey, if the first hash function didn't work, let's try a second hash function. But these are much more easy to understand. Open addressing says if my spot is taken, look for the next available spot, where we have different ways of defining next. I'll go into that in more detail. Chaining is a bit easier is a bit more straightforward. Chaining is actually very popular, and the idea here is that each slot is instead a list, right? Each slot instead is a linked list. And so if you have a collision, like say over here, you would just add it to the end of the linked list. Now, this maybe seems like, how does this still give us a constant runtime? And the answer is that we keep track of the number of items we have, and therefore the number versus the number of slots we have, and we basically try to say, okay, we want to maintain some constant runtime, say like 3 steps, and so we make sure that on average that you're not going to go, that no list is going to make us go more than 3 steps, right? And otherwise, if we do, and if that does happen, we rehash. We just simply do what we do with an array list. We create a bigger array, move everything over, and that all just happens completely blind to the user. Yes, that takes O of n time, but it's what we call O of, now we can say it's constant time amortized. That cost of rehashing is spread out among the cost of the algorithms, and it happens so rare, cost of everything else, and it happens so rarely, we don't, in comparison to the puts and gets, that we don't really have to worry about it. Open addressing is much more interesting, I find, which simply says, hey, you have A is taken, and I want to put B there. That's taken, so I will go to the next available spot. So there's, so this is typical. So next is defined in one of 2 ways, in your text in these lessons. The first way is open addressing with linear probing, which is next is the very literal definition of next. So basically what we'll do is we'll say, okay, I want to put B in here. It's not going to fit. But maybe it looks like this. So you probe each slot until you find the next available slot. Okay? And until you just simply add 1 to your indexes until you get to a slot that is empty, and then you take that. And then when somebody tries to retrieve B, they're saying, well, the hash function says B would be here. So what I need to do is I need to go through and I need to check, okay, is this B? No. This B? No. Is this B? No. Is this B? No. Is this B? Yes. Retrieved. Okay? And again, what we do is we keep it, and I'll get into that in a second, actually. And if it doesn't exist, if we haven't put B in yet, what we'll do is we'll go, okay, none of these are B, and then I hit an empty spot, or I hit a special deleted kind of marker, in which case this is now not there, so, we hit an empty spot. If it was there, we would have seen it, so it's not there, so return key error. Now, the way this works to maintain constant time, regardless of whether we're using open addressing with linear probing or quadratic probing, is that some amount, there needs to always be free spaces for us to basically park our item that we're trying to put in. The way I like to think of it is a parking deck, right? You've probably tried to park at a parking deck where there's basically 1 or 2 slots open, and it takes forever to find that slot, right? It takes forever to park your car there. However, if the parking lot has half the spaces open, it's like you can choose any space you want, right? It's half empty, which is good in this case. And you just basically find a spot almost instantly. So that's what we're doing. That's effectively what we do with space. The hash table maintains maybe like 25% of its space, just simply being free for these insertions, because as it gets fuller and fuller, you'll get there's a formula for how long these lookups will take. Okay, I think I go over it in the video. It's not necessary here. I'm going actually into way more detail than a 5-point question wants, but I feel like it's worth going into.
Gotta earn that 5 points.
All right, the other part is that what if what's the other way? Quadratic probing. Quadratic probing works like this. Say we're trying to put in B, A is there, C, D, E. All right. Quadratic probing says the next available slot will be checked quadratically. So, okay, I'm going to check 1 squared away from our original spot. Okay, that didn't work. I'm gonna check 2 squared away from our original spot. So 1, 2, 3, 4. Aha, took me only 2 probes, right? And the end result of this is actually, what would happen is there's less clumping going on. It's a bit easier. The cost, though, is that technically it takes a bit longer and constant. It's a longer constant time because it requires another multiplication operation when you didn't have one before. Anyway, so in conclusion, for this answer, why do they occur? Because 2 things try to occupy the same, because 2 keys try to get assigned to the same index. That is why they occur. How are they handled? Open addressing, where you look for the next available slot, or linked list, or chaining, which every slot is a linked list, so it can hold multiple things. Yes.
You want both, or do you prefer one or the other?
I mean, in this case, I'd probably give. For full credit, I would want to hear both for this one. Sorry. Okay. What is the worst case runtime for insertion and deletion algorithms in a binary search tree, and why? Okay. The worst case runtime, so we were dealing with average cases for the longest time here, right? The advantage of trees is that they are basically log n on average for everything. Okay? If they are self-balancing binary search trees, which is the one topic I really don't have time to go over, but I wish I did, but there's already so much, and I feel like I'd be really making this class a lot harder if I had to. It would be also a lot more rigorous, but it would be a lot harder if I went over that as well. We have an average log n runtime. Self-balancing binary search trees will make that worst case go to log n as well. That's the reason self-balancing exists, because the worst case runtime for all operations, if you don't, in a regular, just undefined binary search tree, is O of n. Okay? The worst case runtime for insertion deletion algorithms in the binary search tree is O of n. Why? Because depending on how you add stuff, you could get unlucky. The idea for binary search tree is that half the items are going to be in on the left, and half the items are going to be on the right, approximately. If it's balanced, that's going to be that's kind of the idea of it being balanced. You can go left or right, and then basically you would eliminate half your search space every time you go left or right. So if it's not balanced, you're not going to eliminate half your search space. And instead, if it looks something like this, this is not balanced at all, right? If your tree is just some kind of jagged, monstrosity, okay, like that, then all we've done is we've made a linked list with extra steps, essentially, right? That's effectively what your worst case is. You can even be simpler and more direct and say, hey, our worst case would be something like this, which is really, truly a linked list with extra steps, because now not only do we have a linked list structure, a structure that's basically indistinguishable linked list, it also has an extra empty null for every single variable, right? So that's the worst case scenario as to why add and remove could be O of n. If you get, this is a highly contrived situation. Something like this is not, or this being like part of a subtree is not. And this is why self-balancing is a thing. All right. Let's see, and that is it for the review on it. All right, wow. It did take up most of the class time. Okay. Once again, the exam will have a 5-point buffer built in. Let me go ahead and stop recording for a second and